Hi everyone, welcome back to my video about programming in Go. This video is part 3 of the series of the lecture about methods and interfaces. In the first part, we had covered the basics about methods, and in the second part, we covered the basics about interfaces. We also discussed the two built-in interfaces, including the stringers and error. In this part, we will cover more built-in interfaces and also cover the type assertion. Let's start with another built-in interface, io.Reader. This built-in interface is defined in the I/O standard package and represents the read end of a stream of data. The io.Reader interface has a read method which takes a byte slice p as the only argument and reads up to length of p bytes into p. It returns the number of bytes read and an error encounter. The number n of bytes read must be between 0 and length of p. Even if method read returns n less than length of p, it may use all of p as scratch space during the call. If some data is available but not length of p bytes, method read conventionally returns what is available instead of waiting for more. When the stream ends, the read method returns an io.eof error, which is short for end of file error. However, it may return the io.eof error from the same call along with the positive number of bytes read, or return the io.eof error from a subsequent call with n equals 0. Go standard library contains many implementations of this reader interface, including files, network connections, compressor, and ciphers, etc. Packet I/O also defines other interfaces, including writer and read writer. Writer is the interface that wraps the basic write method, which is the opposite operation of the read method of the io.Reader interface. Method write also takes a byte slice p as the only argument and writes length of p bytes from p to the underlying data stream. It returns the number of bytes written from p. So where the number of bytes written must be between 0 and length of p. It also returns any error encountered that caused the write to stop early. Method write must return a non-nil error if the number of bytes written is less than length of p. The interface read writer consists of both the method read from the io.Reader interface and method write from the io.Writer interface. But it can be defined in many other ways besides listing both method signatures directly. One way is to list the interface writer instead of the write method signature, or list the interface reader instead of the read method signature. Another way is to list both reader and writer interfaces instead of the read and write method signatures in its body. This syntax of defining the read-writer interface resembles struct embedding. It lets us name another interface as a shorthand for writing out all of its methods. This is called embedding an interface. Recall that an interface is just a set of method signatures, but that set can be an empty set. The interface with an empty set of methods is called the empty interface. It is denoted by the keyword interface followed by the braces with nothing inside. Because the empty interface is still a data type, you can declare variables of the empty interface type, as in the declaration of variable any in this example. An empty interface variable may hold values of any type. For example, variable any, which is of the empty interface type, can hold an integer value 42 or a string value hello. In practice, the empty interface is used by code that handles values of unknown type. For example, the fempty.print method takes any arguments of the empty interface type so that it allows us to print any kind of data. Another feature related to interfaces is type assertions. A type assertion is a statement that provides access to the underlying concrete value of an interface value. This is necessary because an interface can hold values of various concrete types, and to work with the specific methods or properties of that underlying type, you need to assert its type. There are two forms of type assertions. One form is the single value assertion, which is the highlighted statement here. It's an assignment statement in which the left-hand side is a single variable and the right-hand side is a dot operation with an interface variable before the dot and a concrete type in parentheses after the dot. This statement asserts that the interface value I holds the concrete type t and assigns the underlying t value to the variable little t. If the interface value I does not hold a t value, the statement will trigger a panic. For example, let's declare variable I to be of the empty interface type and let it hold the string value hello. Then the statement s colon equal I dot parenthesis string close parenthesis is an assertion which asserts that the interface value I holds the concrete type string and assigns the string value hello to variable s. So when we print out the variable s, it displays a string hello. The last statement, f colon equal I dot open parenthesis flow64 close parenthesis is also an assertion, which asserts that the interface value I holds the concrete type flow64. But since that's not true, this assertion triggers a runtime panic. Another form of type assertions is the two-value assertion, which is used to test whether an interface value holds a specific type so that the program can avoid panic. A two-value type assertion can return two values. The first returned value is the underlying value of the interface value. The second returned value is a Boolean value that reports whether the assertion succeeded. Note the similarity between this syntax and that of reading from a map. The highlighted statement here is the two-value assertion form. In this statement, if the interface variable I holds a concrete type t, then variable t will be the underlying value of the interface value I, and variable OK will be true. Otherwise, variable OK will be false and variable t will be the zero value of type t, but no panic occurs. For example, suppose variable I has been declared to be of the empty interface type and holds a string value hello. Then the assertion s comma OK colon equal I dot open parenthesis string close parenthesis will assign string literal hello to variable s and assign value true to a variable OK. And the assertion f comma OK colon equal I dot open parenthesis flow64 close parenthesis will assign value false to the variable OK, because the interface value I is not holding a flow64 value. In this case, variable f receives the zero value of the flow64 type. In your programs, you may need to write several time assertions for the same interface value, because an interface value may hold different concrete types. For that purpose, it's more convenient to use type switch, which is a construct that permits several time assertions in series. A time switch is a specialized form of the switch statement, in which the cases specify times instead of values, and those times are compared against the type of the value held by the given interface value. The declaration in a time switch has the same syntax as a time assertion I dot t in parentheses, but the specific time t is replaced with the keyword type. This switch statement tests whether the interface value I holds a value of time t or s. In each of the t and s cases, the variable v, which holds the underlying value of I, will be of time t or s respectively. In the default case, where there is no match, the variable v is of the same interface type as variable I. Here is an example of using type switch. In this example, we define a function do that takes an interface value I as the only argument. The function body has only a time switch statement, which tests whether the underlying concrete value of I is a time int or string. The underlying value of I is assigned to variable v by the expression v colon equal I dot type. In the case v has a time int, it prints out v and v times 2 because a time int allows arithmetic operations such as multiplication. In the case v has a string, it prints out v and length of v because time string allows the string operations like length of a string. In the default case, it prints out the message with the type of v. In the main function, we call function do 3 times with 3 different arguments. The first call is with an int value, which is 21. So the int case is match, and it prints out twice 21 is 42, because 42 is 2 times 21. The second call is with a string value, hello. So the string case is match, and it prints out hello is 5 bytes long. So here 5 is the length of the string hello. The last call is with a bool value, so the default case is executed, and it prints out the message I don't know about type, and then it displays bool as the type of the value true. In the remaining part of this video, I will discuss more built-in interfaces that are useful for handling graphic images. One of those interfaces is the image.Image. Package image defines the image interface as follows. It consists of 3 method signatures. Method color.Model takes no argument and returns a model, which is an interface type defined in package color. Method bounce also takes no argument and returns a rectangle, which is a struct type also defined in the package image. Method add takes 2 int values as argument and returns a color, which is another interface type defined in the package color. An image is a finite rectangular grid of colors values taken from a color model. And method add should return the color of the pixel at a location given by the argument x and y. The method bounce should return the domain for which a method add can return a non-zero color. The image interface is implemented by the struct RGBA in the image package. Recall that the definition of the image interface in the image package uses 2 built-in interfaces, model and color in the color package. Here are the definitions of those 2 interfaces. Interface color has one method RGBA that takes no argument and returns 4 uint32 values, which represents alpha pre-multiplied values for the color. Interface model has one method convert, which takes a color value as argument and returns another color. There are predefined implementations of these interfaces in the color package. The struct type color.RGBA implements the color interface. The variable color.RGBA model is a predefined color of type color.Model. Here is a simple program that shows an example of using methods of the image and color interfaces. In this program, first we create an image.RGBA instance M by calling the image.new RGBA function, which returns a new image.RGBA instance with the given rectangle. In this example code, the given rectangle is created by function image.Rect with arguments 0, 0, 15, 10. Is the rectangle with lower left corner at location 0, 0 and the upper right corner at location 15, 10. Recall that the struct image.RGBA implements the image.Image interface. So variable M is a value of the interface image.Image. Therefore, we can call the methods bounce and method add of the image interface on the image value M. The method bounce of image.RGBA returns a rectangle, and when we display that rectangle, it shows the locations of the lower left corner and the upper right corner. Here we call method add with arguments 0, 0, which returns a color of the pixel at location 0, 0. Then we can call the method RGBA of the color interface. This RGBA method returns the 4 values that represent the alpha pre-multiplied value of the color. In this case, those values are all 0, which represent the fully transparent black color. Instead of using image.RGBA, we can define our own image by implementing the image interface. This example of implementing the image interface is a solution to the exercise from a tour of Go at this link. In this example, we define my image struct type that will implement the image.Image interface. Recall that the image.Image interface has 3 method signatures, so my image must implement all those 3 methods. That means we have to define those 3 methods with my image receivers. In our implementation, method bounce returns an image.rectangle instance created by function image.rect with parameters 0, 0, 280. This is a rectangle with lower left corner at 0, 0 location and with the width of 200 and the height of 80. Method color.Model simply returns the predefined variable color.RGBA model, which is of type color.Model. Method add should return a color.Color value. Since the color.RGBA struct implements the color.Color interface, we can use an instance of color.RGBA as the returned value of method add. The color.RGBA has 4 fields, namely RGBA. All of them are of type io.8. These fields represent the red, green, blue, and alpha values of the color code. The color.RGBA instance returned by our method add has the same value V for the red and green, and the same value 255 for blue and alpha, where the value V equals the multiplication of the x and y arguments of values of the given location. In the main function, we simply create an instant m of my age and call function pick.showImage with m as the argument. Function showImage is defined in the non-standard package pick. It takes a value m of the interface of the image interface type and displays the image m when executed on the Go playground. Here is the image m displayed by this program when it is executed on the Go playground. So that's the end of the video. Thank you for watching, and I hope to see you again in the next video, which is the last part of the series of lecture about methods and interfaces. Thank you.